Yeah, you can start if you're ready. Yeah.
Test. Good afternoon, everyone. Today we'll be doing our final presentation for a smart navigation system for the visually impaired using vision and depth. For our presentation's table of contents, we first have a background on motivation, existing solutions, design iterations and solution evolution, system architecture, implementation, testing and evaluation, results, our working demo, business feasibility analysis, empowerment outcome, and future recommendations. 596 million people worldwide suffer some form of visual impairment, and 43.3 million people are completely blind. Their everyday lives can be very challenging. Existing traditional solutions exist, such as white canes, guide dogs, human assistants, and as reliable as they can be, they suffer from independence.
So now for the motivation, upon our research, we found that current navigation tool suffers from weak performance, limited accuracy, and unreliable real-time obstacle detection or awareness. So we needed dynamically environments. So these gap highlighted that the need for smarter sensing, better timed audio cues, and predictive navigation capabilities.
Now, before diving deep into our own system, we need to actually understand what other other systems actually exist, and why these solutions often fall short. So the system navigation market actually provides promising technologies. However, these technologies are accompanied by certain limitations. So one of the most common assistive devices currently existing is the WeWalk Smart Cane 2. Now, the WeWalk Smart Cane 2 offers multiple helpful features. So it has a GPU for location tracking and navigation, an IMU-based tracking protocol, and an audio feedback and vibration through its smartphone app, as well as ultrasonic sensors for obstacle detection. However, with all these features, it actually is accompanied by certain limitations. So, for instance, the ultrasonic sensors simply at sometimes may not be able to detect small or complex obstacles. Also, obviously, audio feedback is not reliable in noisy environments, and we cannot solely depend on having feedback through vibration because it's not good for precise awareness. Also, for the WeWalk Smart Cane 2, it's not compatible with all smart cane types, and most importantly, most of the functions are heavily dependent on having actually a stable smartphone connection. So with all of these limitations, we move on to the next solution. So another category in this solution is having a small computer such as Raspberry Pi combined with deep learning models for obstacle detection and navigation. And these usually have a camera for visual input, GPS for navigation, and IMU for rotation and movement. However, they are similar to the WeWalk cane. They are also accompanied by some limitations, primarily similar to WeWalk 2. The ultra sensors are not able to detect small, complex objects. Also, environmental factors influence the performance by degrading the accuracy, and most importantly, it's heavily dependent on the actual data set, which leads to generalization, especially in new or unseen environments. And that's where our system actually comes in. So our solution, an AI-powered smart navigation system, designed specifically for reliability, and combines object detection, offline GPS navigation, multimodal feedback, and voice-controlled interaction, all whilst being affordable and scalable. However, with all of these advantages, Okay, so sorry. For our vision, it's to empower visually impaired individuals with a safe, independent, and intelligent mobility tool, a tool that doesn't struggle in real challenging environments that are unpredictable, and a tool that is affordable and scalable, and a tool that doesn't simply rely on having a smartphone connection.
Now moving on to our design iterations and solution evolution. Our initial setup with the Jetson Nano was using Ubuntu 18 and Python 3.6. Upon integrating our voice pipeline, we faced some difficulties as Whisper, the OpenAI model, which allows us to use the speech to text, required Python 3.8. So what we did was update our Ubuntu to Ubuntu 20, which then broke all our GPU drivers. So our choice of Jetson Nano became absolutely useless. What we did then was search online, and we found a community image, community Ubuntu image on GitHub, which supports Python 3.8, preserving the Jetpack drivers, CUDA, and PyTorch compatibility. This allowed us to seamlessly install most of the AI models we have in our setup.
So even after solving the software compatibility issues, we faced another big wall, 4 gigabytes of RAM, which at first sounded promising. However, when it actually came down to implementing and integrating the pipelines, the Whisper and NLP modules alone took the entire space. And so even after aggressive optimization efforts, it just proved to be insufficient. And so comes our breakthrough, achieving efficient resource management through client-server architecture.
We use gRPC to send data from the client, which is the Jetson Nano. We send data using from the sensors to the servers, which then gets processed by the server in order to return a response based on whatever feature the user is using. We have a bi-directional communication between the client and the server, where the client is Jetson Nano and the server is what we used in order to process most of these data.
Okay, so for now, we have two main processing pipelines. The first, it is the navigation stack, where we got to go through 3 main iterations. The first one, we got to focus on how we can implement the full pipeline on the Jetson, choosing state-of-the-art techniques. But due to the hardware, due to the resources constraints, we couldn't do that. So we then went to a more of a lightweight approach, where we removed the complex models, and we got to use more of a lightweight models, but still we couldn't get to fit the navigation stack and the voice module. So we finally got to set on a cloud to server architecture, where the client, the Jetson Nano, sends to the server the required data to process the navigation stack. And for the voice module, we got to firstly do it all on the Jetson, but still we couldn't do that. So we then went to the same cloud to server architecture. So then here we got to actually implement the 3D object detection and the SLAM. Okay. And then we try to replace the complex model that we already implemented, like the 3D. We got to switch it are we going to replace it with the 2D? And are we going to implement the SLAM on the JSON? And we implemented them. Are we going to implement them on the JSON? But we still we couldn't get to fit it. Okay, so now for the final solution, we can see that the JSON gets to publish the camera and the depth data to the server, and the GPS, are we going to send it to the server, or to then the server gets to run the obstacle avoidance and the 2D object detection, and then send the response back to the server.
Now let's look at the voice system module. We had similar iterations similar to the navigation stack. So the first iteration was having all the models on the Jetson Nano, the voice activity detection, the speech to text, the NLP, the text to speech. This gave us no dependence on the internet, and it was a self-constrained system on the device. However, this architecture, it used most of the RAM and the CPU of the Jetson, which was hard to have more components and modules on the Jetson Nano. So this pushed us to go to the second iteration, which uses a hybrid cloud architecture, which is the iteration 2, which is hybrid edge cloud audio architecture. So how it works? So we have a Jetson side and the server side. The Jetson side, we have a small model, the voice activity detection. This detects the speech segments and sends it to the server side. And on the server side, it runs all the pipeline. And then the output is then returned back to the speaker for confirmation. So by utilizing this architecture, we reduce the load of the Jetson. So for our proposed solution, for the navigation stack, we'll go with the third iteration, as Yahya mentioned, for its advantages. And for the voice system module, we'll go with the second iteration, since it reduces the load of the Jetson Nano.
All right, so for the system architecture, let me walk you through the technical implementation of our system, starting with the overall architecture. So our navigation solution is structured around two core pillars, the software layers and the hardware integration, ensuring a clear separation of responsibilities while maintaining smooth communication across components. So the software layer manages the computation, data processing, and decision makings, whereas the hardware layer provides a physical interface for sensing the environment and delivering users feedback. So let's explore each part in detail. So as for the hardware architecture, we have the NVIDIA Jetson Nano at the core of our solution or system, connected to a power supply, in our case, a power bank. It also has a microphone for the user to be able to communicate with the system, sending him commands and for navigation. Also, we have a GPS to send the coordinates of the user, and then my colleague Sabri will explain this part in much details later on. We also have an RGBD camera that helps in the object avoidance and object detection modules we have. Also, a Wi-Fi and Bluetooth modules, a Wi-Fi for the client or the NVIDIA Jetson Nano to be able to communicate with our server. And also we have a small speaker that needs the Bluetooth modules to send the audio feedbacks for the audio feedback for navigation and object avoidance. And finally, we have a haptic feedback device that we will also talk about in much details later on. So moving on to the hardware architecture.
Okay, so now for the software architecture, we can see that we have the client to server architecture that I got to show you, and other sensor data and acquisition layer, which gets to collect the other required data and sends it to the server. And then we can see other data processing layer, which gets to process the layer and remove the noise in the voice to activity detection part, and then send it to the server.
Now moving on to our implementation, starting with the voice system module. As Sabri explained in the architecture, what happens first is the mic catches the input. The input is taken to the voice activity detection, where it detects if the sound was either ambient noise or was it a sound coming from a person. Then it moves on to the speech to text, where the voice is transcribed and then taken to the NLP. The NLP plays a very important role where it gets the intent of the transcription and gets the slots of the text. And based on the intent we took from the NLP, we use it in the action and planning. And based on the intent, we would do a certain action, which is then we move on to the text to speech, where we generate a response from the system based on the action and planning, which is then taken to the speaker to the system output.
So another big part of this final phase implementation was the 2D object detection. So our navigation aid system now uses YOLO version 8 Nano. It's also important to mention that this model is pre-trained on the extensive COCO dataset. So this helps the user to be able to identify any obstacles in their path. It's also not just about the object detection, it's also about sending important visual information to the actual system so that it's able to make informed, immediate, and intelligent navigation decisions to ensure seamless navigation. So, for the obstacle avoidance, which builds on the 2D object detection, our dynamic window approach module continuously processes depth data and sensor data to be able to recommend the safest possible path for the user while navigating. Also, whenever the user encounters any obstacle, it doesn't just stop. It automatically reroutes to the next safest possible path for the user.
Now let's look at the haptic feedback. So first, the connections. First, we had a breadboard setup, which was really complex, the wiring, so it was really hard to integrate. So we moved to a single-side PCB, which was easier for us to integrate to other modules. So how does the haptic feedback work? So basically, we have 4 sensors on the user's hand, located top, middle, right, and left. They help the user move to the other directions according to the obstacle they will encounter. Also, we support combined patterns to move diagonally, such as northeast or northwest. Also, we integrated this haptic feedback with the navigation stack and the voice system module for real-time feedback. So next is the GPS receiver, which is used for outdoor navigation. It provides us with the real-time localization that helps the user to move to the intended destination. So how does it work? So firstly, there's a client side and the server side. On the client side, the Jetson, it sends the GPS coordinates to the server side using gRPC, and then the server returns back with the directions that the user needs to move according to the user's current position. So we also integrated this GPS receiver with the voice system module for confirmations, and also the navigation stack to help the user to reach the required destination.
Now that we're done with the main system design and the core features, we move on to testing and evaluation. So this section is very crucial in evaluating the performance of our system in real time outside environments, especially those that are dynamic and unpredictable. So for the user setup, in order to evaluate our system, we have we made a wearable vest. We made a wearable vest to allow user movement in parallel to the actual system operating in real time. We have Jetson Nano in the back of the vest, connected to a real sense camera. And the camera is mounted on the chest level of the user in order to view, give a full view or full picture of the actual user navigating with his hands free. And also we have third thing, which is vibration, which confirms haptic feedback placed on the user's arm. So this basically mimics how a user would experience, what a visually impaired user would experience in a real-time environment outdoors.
Now for the obstacle avoidance, as you can see in these pictures, the obstacle avoidance model clearly identified that there are obstacles in front of it with some parameters like the center depth and the IO rate, and it tells the user to move direction to avoid this obstacle.
Unfortunately, the sound is not is on the lab. The sound isn't being played. Oh, I can explain what was going on in the video. So here, this is a video where Ziad talks to the system and asks that he wants to go to place X. And then based on that, it reports back, it responds back to Ziad and says that it will start calculating the direction or the GPS directions to the place that Ziad specified. Now these are 4 screenshots. Each screenshot shows the progress of the GPS navigation being in play. What happens here in the first screenshot, it shows us at around the quick, and then we progressively move towards Busgate.
Okay, so now for the results, we can see that the current utilization of CPU, it is around 98%. So we can see how that the current implementation we got to barely fit other solution out to the resource or constraint that we have. And we can see that the memory utilization, it is around 60%. And for the latency, we can see that the frame compression from the Jetson side, it is minimal. And so that, and we can see that the voice activity detection latency on the Jetson, it isn't that much.
Now let's look at the working demo. So please, can you watch this video? Now let's analyze this video first, so please can you watch it again? So let's pinpoint at this time frame. So at this time frame, the user, there's an obstacle in front of him. So the obstacle avoidance model clearly identified that there's a person and the direction needs to change. So as shown here at the top right image, it tells the user to move to the northeast direction using the haptic feedback vibration. So at the end, the user actually changes his direction to avoid the obstacle. And here's the GPS layer. So unfortunately, there's no sound. But what should happen is that the user will set the destination he wants to go to, and then the system will tell him to move right, move forward to reach the final destination.
Now, to evaluate our idea from both a business aspect and a technical aspect, we deducted a SWOT analysis. So for our system, our strengths are obviously indoor-outdoor navigation, affordability, an intuitive voice-controlled experience, and the system mostly relies on advanced AI perception for a more safe mobility in comparison to already existing solutions. Our weaknesses are temporary, things like battery limitations requiring an initial hardware setup, and the opportunity is so massive because you have almost 600 million visually impaired users around the world, and that's why governments and NGOs are always keen on investing in accessibility technologies. For the final thing, for the threats, threats include competitors advancing their smart cane features, hardware supply cost fluctuations, and assistive devices having to pass regulatory measures.
So our target customers would be the visually impaired individuals that want more independence and want more control over their everyday navigation. We also see a huge opportunity when it comes to collaborating with NGOs and government bodies that are leading accessibility initiatives. As for our revenue streams, we identified that they will be mainly generated through device sales, licensing and partnerships, and finally data analytics.
Now, as we look beyond the technical development, we need to understand our actual system. So first of all, in terms of we need to understand the broader impact and our long-term potential. So in terms of scalability and future growth, our system is built on modular design. So we could simply add new sensors, new features, new models without having to basically redesign from scratch. Regarding the adoption strategy, our adoption strategy primarily focuses on pilot programs and partnerships. So, for instance, collaborating with NGOs to actually integrate our real system in community centers and evaluate performance and receive actual feedback from the visually impaired users. So it's actually a practical implementation rather than just a theoretical one. And for the social impact, we care about the technological impact as well as support for the actual visually impaired user. So it enhances independence and mobility for visually impaired users and increases their confidence.
Now here, as you can see, the competitive landscape, we have a table demonstrating the edge that our system or our solution have over the existing smart canes or other solutions existing in the market right now. So as for the features, our solution has an indoor and outdoor navigation, hands-free voice interaction, hazard detection, both ground and overhead, and finally a universal cane compatibility. Moving on to the prices.
Okay, so now up for the hardware, we got to price it on other US dollars, and for the labor cost, we got to price on the Egyptian pound. So we got to so for around 20 clients, we can price for a per customer at around 83,000 pounds.
And now finally for the empowerment outcomes, we have a functional MVP and we have successfully developed a working prototype of the complete system. Also, we have a draft of the research paper that needs it needs to be finalized that documents the methodology and the result, highlighting the contribution to assistive navigation and real-time robotic systems. Okay, so for future recommendations, first, we have found that a fully on-device navigation, so we need to optimize perception and planning to remove cloud dependencies and ensure offline reliability. Also, we need to optimize the indoor SLAM, implementing a lightweight SLAM for indoor environments, as well as enhancing the obstacle awareness, and by adding models to detect stairs, holds, low height obstacles, and narrow pathways more accurately. Finally, we found that it also needs a similar. We also need to make the hardware smaller and remove extra cables and increase battery time. Thank you.
Thank you.